alpha blobs. In 2000, a team of astronomers led by Charles Steidl used the Keck Observatory in Hawaii to peer into the deep universe and found something enormous glowing in the darkness between galaxies. It was a vast cloud of hydrogen gas, radiating light at a very specific wavelength of 121.6 nanometers, the so-called Lyman alpha emission line, and it was bigger than most galaxies. They called it a Lyman alpha blob, and they had no satisfying explanation for what was making it shine. Before this discovery, astronomers understood that gas clouds in space could glow when energized by a nearby source, a hot young star, a quasar, something pumping out ultraviolet radiation. The rules were simple. Light a fire, the gas glows. No fire, no glow. What Steidl's team found sitting roughly 11 billion light-years away in the constellation Aquarius, in a region of sky catalogued as SSA22, appeared to break those rules entirely. The largest of these blobs exceed 400,000 light-years across, several times the diameter of the entire Milky Way. They are not galaxies. They contain no structure, no spiral arms, no stellar nurseries you'd expect to find. They are just enormous, shapeless clouds of gas radiating enormous amounts of energy. And in a number of confirmed cases, astronomers have searched exhaustively for a central power source bright enough to explain the glow and found nothing adequate. Theories have been proposed and contested for 2 decades. Some blobs may be powered by hidden quasars, buried deep inside veils of dust. Others might be lit by intense bursts of star formation occurring within them. A more exotic proposal suggests the glow comes from cold gas streams falling inward along cosmic filaments, releasing gravitational energy as light. Each explanation accounts for some blobs, but not all of them, and the debate has never been fully resolved. These objects have been floating in the universe for billions of years, glowing with the energy of 100 billion suns, and we still cannot agree on what is generating that light. For structures this large and this luminous, that is a remarkable admission. What else might be glowing out there in the dark between galaxies too vast and too strange for our current understanding to name? Number 11, the cosmic web filaments. When astronomers completed the first major surveys of the large-scale structure of the universe in the 1980s and 1990s, they expected to find galaxies distributed more or less evenly through space, clustered perhaps, but without any overwhelming pattern. What the CFA redshift survey, and later the 2DF galaxy redshift survey revealed instead, was something that looked disturbingly organic. A vast three-dimensional web of filaments, sheets, and nodes connecting galaxy clusters across distances of hundreds of millions of light-years, with enormous empty voids in between. The cosmic web had been theoretically predicted by Soviet cosmologist Yakov Zeldovich as early as 1970, but seeing it confirmed in real data was a different experience entirely. The universe, on its largest scales, resembles nothing so much as a biological nervous system, or a fungal network, with matter concentrated along thin threads and galaxy clusters sitting at the intersections like neurons at a synapse. The spaces between those threads, the voids, make up roughly 80% of the total volume of the observable universe. What took decades longer to confirm was what those filaments actually contain. For years, cosmologists knew that the ordinary matter they could observe, all the stars and gas in all the galaxies, added up to far less than the amount predicted by Big Bang nucleosynthesis models. Roughly half of all ordinary matter in the universe was simply missing. In 2020, separate teams using Arecibo satellite data and Sunyaev-Zeldovich effect measurements finally confirmed what had long been suspected, that missing matter was hiding in the filaments, in a form called the warm-hot intergalactic medium, gas so diffuse and so faint that it had evaded detection for decades. The Hercules Corona Borealis Great Wall, identified by Istvan Horvath, John Hakala, and Zsolt Bogoli in a 2014 paper published in Astronomy and Astrophysics, represents a filamentary clustering of gamma-ray bursts stretching an estimated 10 billion light-years across, a scale so large that standard cosmological models say it should not be able to exist. The universe has not been around long enough for gravity to assemble anything that enormous. That finding remains actively debated, but it has not been dismissed. Half of all the ordinary matter in existence spent decades hiding in threads of near-invisible gas, and we only confirmed its location in 2020. The skeleton of the universe was built before any star was born, assembled from dark matter and physics we are still learning to read. What we can be certain of is this: the space between galaxies is not empty, and it is far stranger than it first appeared. Number 10. Intergalactic magnetic fields. In 2010, astrophysicists Andrei Naranov and Yevgen Vovisi published a paper in Science that made a quietly alarming claim. Using data from NASA's Fermi Gamma Ray Space Telescope, They had detected evidence of magnetic fields threading through the cosmic voids between galaxies, in regions of space so empty that there should be almost nothing there at all, certainly nothing capable of generating or sustaining a magnetic field across millions of light years. Magnetic fields, as physicists understand them, require moving charged particles. You need current, you need matter, you need activity. The void between galaxy clusters has almost none of these things. Its density is so low, roughly 1 atom per cubic meter in the emptiest regions, that it qualifies as a better vacuum than anything we can produce in a laboratory on Earth. By every conventional expectation, organized magnetic fields in such an environment should not persist. Yet the fields are there. They are extraordinarily weak, measured in femtotesla, a unit so small it is a quadrillion times weaker than a refrigerator magnet. But they extend across staggering distances, and crucially, they have been detected in the deepest voids, far from any galaxy that could plausibly have seeded them. Their orientation shows a degree of large-scale coherence that passive diffusion over cosmic time cannot easily explain. The leading theories divide into two camps. The first holds that these are primordial magnetic fields, born in the first seconds after the Big Bang, perhaps during a phase transition in the early universe and stretched to cosmic scales by expansion ever since. If true, they predate every star, every planet, every galaxy that has ever existed. The second camp argues they were generated by early stars and quasars, and then transported outward by galactic winds and jets. Neither explanation has achieved consensus, and dedicated observing campaigns using the Square Kilometer Array are designed to eventually distinguish between them. In the emptiest places in the observable universe, an invisible architecture of magnetic field lines is threading through the void, ancient beyond reckoning, and we do not know where it came from. Something organized those fields, either in the first moments of creation or through a process we have not fully traced, and it has been maintaining that structure across billions of light years ever since. Number 9. Rogue stars between galaxies. In the 1990s and early 2000s, observations with the Hubble Space Telescope began revealing a faint diffuse glow between the galaxies of clusters like Virgo and Coma, a glow that did not belong to any individual galaxy. When astronomers analyzed that light carefully, they reached a conclusion that was difficult to process. There were stars out there, billions of them, drifting entirely alone through the intergalactic void, unbound to any galaxy, lit by no galactic core, orbiting nothing but the slow pull of the cluster's collective gravity. Galaxies had always been assumed to be the containers of stars. Stars form inside galaxies, live their lives inside galaxies, and die inside galaxies. The idea of a star existing permanently outside any galaxy, in a region of space where the nearest other star might be thousands of light years away, had seemed like an edge case at most. It turned out to be one of the largest populations of stars in the universe. Current estimates suggest that in rich galaxy clusters, between 10% and 50% of all stars may exist outside any individual galaxy, depending on the cluster's history of mergers. The Virgo cluster alone is estimated to contain hundreds of billions of these intergalactic wanderers. James Webb Space Telescope observations, beginning in 2022, have dramatically sharpened our picture of this intercluster light, revealing its distribution in unprecedented detail and confirming that the phenomenon is both widespread and enormous in scale. These stars were almost certainly ejected during galaxy mergers, gravitational interactions so violent that individual stars were flung outward at speeds of hundreds of kilometers per second, sailing beyond the edge of their home galaxy and into permanent exile. The process is ongoing. Every time two galaxies collide and merge, more stars are scattered into the void. They carry with them whatever planetary systems formed around them, those planets now drifting in regions of space where no galaxy is close enough to cast more than the faintest smear of light. If planets orbit those rogue stars, and there is no reason to assume they do not, they exist in a darkness with no equivalent anywhere inside a galaxy. Their sky would be essentially black. No Milky Way stretched across the night, no neighboring stars visible to the naked eye, just the faint distant light of galaxy clusters, hundreds of millions of light years away. Whatever might live on such a world would have very good reason to believe the universe contained almost nothing else. Number 8. The intergalactic medium's temperature problem. The gas that fills the vast spaces between galaxies, a thin, tenuous plasma known as the intergalactic medium, should by every straightforward calculation be cold. There are no stars out there burning to heat it. There are no nuclear reactions, no shock waves from nearby supernovae, no obvious energy sources of any kind. Simple models predict temperatures in the tens of thousands of Kelvin at most, consistent with the faint ultraviolet glow of distant quasars slowly ionizing the hydrogen. But when astronomers began measuring the intergalactic medium directly, they found something considerably more alarming. The temperature of the IGM varies dramatically by region, but in many areas it runs to hundreds of thousands or even millions of Kelvin, far hotter than models of simple photoionization could account for. The discrepancy became known informally as the IGM temperature problem, and it has occupied cosmologists since the 1990s. Something is pumping enormous quantities of heat into the void between galaxies, and for a long time, nobody could convincingly identify the source. The leading candidate today is a process called helium reionization. Helium, unlike hydrogen, requires much more energetic radiation to strip its second electron, and the objects capable of producing that radiation are quasars. A 2019 study using the cosmic origin spectrograph aboard the Hubble Space Telescope provided strong supporting evidence that a burst of helium reionization driven by quasar activity between about 3 and 4 billion years after the Big Bang heated the IGM substantially. A separate mechanism, Blaser heating, was proposed by Mhoy Avery Broderick and colleagues in 2012, suggesting that the high-energy gamma-ray jets from active galactic nuclei deposit heat directly into the surrounding intergalactic gas. Neither mechanism alone fully resolves the temperature budget. The two processes together bring models closer to observations, but significant uncertainties remain, particularly in the densest filament regions where the temperature excess is most pronounced. The intergalactic medium is also not uniform. It has a complex thermal structure shaped by the history of cosmic reionization, galactic feedback, and processes that simulations are only beginning to reproduce with reasonable accuracy. The void between galaxies is not cold and dead as it should be. Something has been heating it for billions of years, working through mechanisms we have identified but not yet fully understood, maintaining temperatures in regions of near-perfect emptiness that rival the outer layers of a star. The universe, it seems, does not allow its empty spaces to simply go cold. Number 7. Fast radio bursts. On July 24, 2001, a burst of radio energy crossed billions of light-years of intergalactic space and was captured by the Parkes Radio Telescope in New South Wales, Australia. Nobody noticed for 6 years. It was astronomer Duncan Lorimer who found it in 2007, sifting through archival data with his student David Narkovich. And when he saw the signal's dispersion, the way its different frequencies had been spread out by the electrons it had passed through on its journey, he realized it had come from far outside the Milky Way. In a few milliseconds, whatever produced this burst had released more energy than the sun emits in days. Fast radio bursts, FRBs, were initially so extraordinary that significant portions of the astronomical community suspected they were interference, some earthly contaminant masquerading as a cosmic signal. The Parkes telescope had been fooled before. It took years of additional detections and the eventual real-time capture of bursts by multiple independent observatories to settle the debate. They were real, they were extragalactic, and they were happening constantly. The Chime Radio Telescope in British Columbia, Canada, began operations in 2018 and rapidly transformed the field, detecting hundreds of FRBs and revealing a phenomenon far more diverse and complex than anyone had anticipated. Some bursts repeat, firing again hours or days or months later. Others have been detected only once. Some repeat with eerie regularity, like FRB 180916, which fires in a 16.35-day cycle, suggesting an orbital or rotational clock of some kind. The source distances range from hundreds of millions to billions of light-years, scattering them across a vast span of cosmic time. In 2020, a breakthrough came from inside our own galaxy. An FRB was detected originating from SGR 1935+2154, a magnetar, a type of neutron star with an extraordinarily powerful magnetic field, located about 30,000 light-years away. This was the first time a source was directly identified, and it strongly supported magnetars as at least one type of FRB progenitor. But magnetars cannot easily explain the full diversity of observed bursts, particularly those with precise periodic behavior, and the full taxonomy of what produces these events remains an open question. Every day, by theoretical extrapolation, hundreds of thousands of fast radio bursts cross the observable universe in all directions. We have cataloged only a tiny fraction of them, and even that fraction contains mysteries that our best models cannot fully explain. The universe has been producing these millisecond screams of energy since long before Earth existed, and we have only just learned to listen. Number 6. The supervoids. In 2004, astronomers analyzing data from NASA's WMAP satellite which had produced the most detailed map yet of the cosmic microwave background, noticed something wrong with a patch of sky in the southern constellation Eridanus. The CMB, the ancient afterglow of the Big Bang, should be very nearly uniform across the sky with only tiny temperature fluctuations of a few millionths of a degree. In this particular region, however, the temperature was measurably and stubbornly lower than it should be, by approximately 70 microkelvin. They called it the cold spot, and it has not been explained satisfactorily since. The cosmic microwave background is the oldest light in the universe, emitted roughly 380,000 years after the Big Bang, and carrying encoded in its temperature variations the seeds of all the structure that followed. Anomalies in it are taken seriously, because this light has been traveling toward us for nearly 13.8 billion years, and anything that disturbed it left a mark that persists. A cold spot of this magnitude and angular size sat at the edge of what standard cosmological models predicted could exist by chance. In 2015, a team led by Istvan Sapudi at the University of Hawaii identified a supervoid aligned with the cold spot, a region of space approximately 1.8 billion light-years across, containing roughly 20% fewer galaxies than a typical region of its size. Published in monthly notices of the Royal Astronomical Society, this was the largest supervoid ever identified, and it offered a potential explanation. Photons of light lose energy as they travel through large empty regions, a phenomenon called the integrated Sachs-Wolf effect, and this energy loss would show up as a cold patch in the CMB. The numbers, however, did not fully add up. The supervoid accounts for some of the temperature deficit, but not all of it. The cold spot is colder than the void alone can explain. The remaining discrepancy has attracted increasingly exotic proposals. Some researchers have suggested the cold spot might be a gravitational imprint left by a collision between our universe and an adjacent bubble universe during the inflationary epoch, a bruise in the fabric of the CMB left by contact with something outside our observable cosmos. This hypothesis is considered fringe by most cosmologists, but it has not been formally ruled out, and the Planck satellites data confirm that the cold spot's anomaly persists even in the most sophisticated analysis. A billion light-year hole in the universe, in a direction where the oldest light in existence runs measurably cold, and our best models still cannot fully account for the temperature of that silence. Whatever explanation eventually emerges will need to be something genuinely new, because everything we currently have falls short. Number 5. Dark matter and the invisible scaffolding. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford sat with data from the Kitt Peak National Observatory in Arizona and measured how fast stars were orbiting the centers of galaxies. According to Newtonian gravity and everything known about the distribution of mass in those galaxies, stars at the outer edges should be moving more slowly than stars closer to the center, just as the outer planets of our solar system orbit the sun more slowly than the inner ones. They were not. Stars at the edges were moving just as fast as stars near the core, sometimes faster. The galaxies should have been tearing themselves apart, and they were not, because something invisible was holding them together. That invisible something was not a new idea by the 1970s. Swiss astronomer Fritz Zwicky had proposed in 1933 that galaxy clusters contained far more mass than their visible stars could account for. But Rubin and Ford's rotation curves turned the hypothesis into a crisis. Galaxy after galaxy showed the same pattern. The mass that gravity required to explain the motion was simply not there in any form that emitted or reflected light. Something dark, something enormous, something unknown was doing the work. Today, dark matter is estimated to make up approximately 27% of the total energy content of the universe, compared to just 5% for all ordinary matter, every star, planet, gas cloud, and atom that has ever been observed. In the intergalactic context, dark matter forms the scaffolding of the cosmic web itself, the invisible filaments along which galaxies cluster, the unseen halos that surround every galaxy, the gravitational backbone of all large-scale structure. The most direct evidence came in 2006 from observations of the Bullet Cluster, two galaxy clusters that had collided, published by Douglas Clow and colleagues. Gravitational lensing maps showed the mass, and therefore the dark matter, had separated from the hot gas during the collision, drifting ahead of it like a ghost stepping through a wall. Despite 5 decades of increasingly sophisticated searching, dark matter has never been directly detected. The Xenon 1T experiment in the Gran Sasso laboratory in Italy, one of the most sensitive detectors ever built, found nothing. The Large Hadron Collider at CERN has found no particle that fits the required profile. Proposals for what dark matter might be, WIMPs, axions, sterile neutrinos, primordial black holes, continue to multiply and continue to go unconfirmed. Every candidate has survived only because it has not been decisively ruled out, not because it has been found. The architecture of the entire universe Every filament, every galaxy cluster, every structure that has ever formed is built on a foundation of something we cannot see, cannot touch, and cannot detect with any instrument yet devised. It outnumbers ordinary matter by more than 5 to 1. It is everywhere, and after 50 years of searching, we do not know what it is. Number 4. Quasars, the most violent objects in the universe. In 1960, astronomer Martin Schmidt was working at the Palomar Observatory in California, studying the optical counterpart of a radio source designated 3C273. It looked, to every other astronomer who had examined it, like an unremarkable star. Schmidt analyzed its spectrum and felt the ground shift beneath him. The spectral lines were shifted so dramatically toward the red end of the spectrum that the object had to be approximately 2.4 billion light-years away. For a point of light visible to a ground-based telescope at that distance, it had to be producing more energy than an entire galaxy of hundreds of billions of stars, from a region of space no larger than our solar system. The class of objects Schmidt had identified, quasi-stellar objects, or quasars, turned out to be the most energetic sustained phenomena in the observable universe. They are powered by supermassive black holes, actively consuming surrounding material, drawing in gas and dust and stars at such enormous rates that the infalling matter heats to millions of degrees, and radiates across every wavelength, outshining everything else in their host galaxies by factors of hundreds or thousands. They are not rare. Astronomers have cataloged over 1 million of them, scattered across the observable universe, most of them burning brightest in the distant past, when the universe was young and gas was abundant. In February 2024, a team led by Christopher Wolfe published results in Nature Astronomy, confirming that a quasar designated J05294351 is the most luminous object ever measured, with a brightness approximately 500 trillion times that of the Sun. The black hole powering it consumes the equivalent of 1 solar mass every single day. Its light, currently reaching our telescopes, left the object when the universe was roughly 1.5 billion years old. We are seeing something that existed in a universe radically different from the one we inhabit now. And even by that universe's extraordinary standards, it was exceptional. Quasars do not merely shine, they reshape the cosmos around them. The jets they launch, beams of magnetized plasma accelerated to near the speed of light, can extend for millions of light years into the surrounding intergalactic medium, injecting energy equivalent to trillions of supernovae into the gas that would otherwise collapse to form new galaxies. This process, quasar feedback, is now understood to be one of the primary mechanisms by which the universe regulates star formation across cosmic time. The violence happening in the cores of these objects is not local. It echoes across the entire intergalactic environment. The most powerful engines in the universe have been actively rewriting the intergalactic medium for billions of years, determining where galaxies could form and where they could not, heating the cosmic web, launching jets millions of light years long, and we still do not have a complete physical explanation for how a black hole generates and sustains those jets. The object that Schmidt found hiding in plain sight as a dim star has turned out to be a force that shaped the universe you live in. Number 3. The Hercules Corona Borealis Great Wall. In 2013, astronomers Istvan Horvath, John Hakala, and Zsolt Bagoli were mapping the distribution of gamma-ray bursts across the sky, using these extraordinarily powerful explosions as tracers of where matter concentrates in the distant universe. Gamma-ray bursts are visible across billions of light years and mark the locations of massive stars collapsing or neutron stars merging, making them useful probes of large-scale structure. What the team found in a region of sky spanning the constellations Hercules and Corona Borealis, published in Astronomy and Astrophysics in 2014, was a clustering of bursts so pronounced and so vast that it violated one of the most fundamental assumptions of modern cosmology. That assumption is called the cosmological principle. The idea that on sufficiently large scales, the universe is homogeneous and isotropic, meaning it looks roughly the same in all directions and at all locations. It is not a minor working assumption. It is the foundational premise on which virtually all of modern cosmological modeling rests. Without it, the equations that describe the expansion of the universe, the formation of structure, and the behavior of dark energy become dramatically more complex, possibly intractable. The cosmological principle sets a theoretical upper limit on how large any structure in the universe can be, approximately 1.2 billion light-years, beyond which the universe simply should not show coherent organization. The Hercules Corona Borealis Great Wall is estimated to span approximately 10 billion light-years. That is not a rounding error. It is roughly 1/9 the diameter of the entire observable universe. A structure of this scale requires not only matter to be arranged over extraordinary distances, but time for gravity to have assembled that arrangement. The universe has existed for 13.8 billion years. There has not been enough time, by standard physics, for anything 10 billion light years across to have organized itself into a coherent structure. And yet the clustering is there. The finding is debated, and that debate is important to acknowledge. The structure is identified through a statistical excess of gamma-ray bursts, not through direct imaging of the galaxies themselves. Some cosmologists argue the clustering may reflect observational bias or an insufficient sample. Others have attempted to confirm the structure through independent methods with mixed results. It has not been formally accepted as a definitive physical structure by the full cosmological community, and it has not been dismissed either. It persists in the literature as a serious and unresolved anomaly. If the Hercules Corona Borealis Great Wall is real, it does not merely challenge the cosmological principle, it breaks it. And a universe that breaks its own foundational rule at sufficient scale is a universe whose governing equations may need to be rewritten from the ground up. The most disturbing possibility is not that we found something big. It is that we found something that should not exist, and we cannot yet say with certainty that it does not. Number 2. The axis of evil. In 2003, the WMAP satellite delivered what was supposed to be the definitive map of the cosmic microwave background, the ancient light from 380,000 years after the Big Bang, a snapshot of the infant universe encoding the seeds of all structure to come. Cosmologists expected to find a map consistent with isotropy, a universe with no preferred direction, no special axis, no orientation, its fluctuations scattered randomly across the sky. In 2005, Kate Land and João Magejo of Imperial College London published a paper in Physical Review Letters announcing what they called, with deliberate provocation, the axis of evil. The largest features of the CMB, its quadrupole and octopole moments, the broadest temperature patterns visible across the whole sky, were aligned with each other, and aligned with the plane of Earth's orbit around the Sun. The cosmological principle demands that the universe look the same from everywhere, that no location and no direction be special. Our solar system is an infinitesimally small speck in an ordinary galaxy in an ordinary region of space. There is no physical reason, under any standard model, why the largest structures in the observable universe should show any relationship to the plane of our planet's orbit. The probability of such an alignment occurring by chance was estimated at less than 1%. It was, and remains, deeply strange. The anomaly was not a WMAP artifact. The Planck satellite, a more sophisticated instrument operated by the European Space Agency, released its CMB maps in 2013, 2015, and 2018, each time with improved sensitivity and refined foreground removal. The axis of evil was still there. Every major systematic error that could plausibly explain it has been investigated and found insufficient. The alignment of the CMB's largest scale features with the ecliptic plane has survived more than 2 decades of scrutiny and has not gone away. Proposed explanations range from the mundane to the extraordinary. Some researchers suspect residual foreground contamination from local structures in our galaxy or solar system. Others have suggested the universe may have a non-trivial topology, a specific shape, perhaps a finite torus or a more exotic geometry, that would impose a preferred direction on the CMB. A small number of theorists have proposed it as evidence for anisotropic cosmological models, universes that are not the same in all directions at the fundamental level. None of these explanations has achieved consensus. What has been written into the oldest light in the observable universe at the very largest scales we can measure appears to know where we are. That is not supposed to be possible. And the fact that it persists, confirmed and reconfirmed across 2 generations of satellite observations, unchanged by every attempt to explain it away, means that whatever lies between and beyond the galaxies of our cosmos may be organized in ways our current physics cannot yet describe. What comes next on this list is even more fundamental because, unlike the axis of evil, which might eventually be explained by something exotic but local, number 1 is a force operating everywhere in the universe right now, and we have no idea what it is. Number 1. Dark energy. In 1998, 2 independent teams of astronomers set out to measure how quickly the expansion of the universe was slowing down. The expectation was unambiguous. The Big Bang had sent matter flying outward, and gravity, the universal attraction of everything for everything else, was breaking that expansion. The only question was whether gravity would eventually halt the expansion and reverse it into a big crunch, or whether the universe would expand forever but at an ever-decreasing rate. Both teams used Type Ia supernovae as standard candles, explosions of such consistent intrinsic brightness that their apparent faintness revealed their distance with precision. Saul Perlmutter's Supernova Cosmology Project and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, collected their data independently, ran their analyses independently, and arrived at the same answer. The expansion was not slowing, it was accelerating. Something was pushing the universe apart with increasing force, and it was winning against gravity across every distance scale large enough to matter. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011. The thing they found was named dark energy, and it has refused to be understood ever since. Dark energy constitutes approximately 68% of the total energy content of the universe, confirmed to that precision by the Planck Satellite Collaboration's 2018 results. Ordinary matter, everything made of atoms, every star, planet, gas cloud, and living thing, accounts for roughly 5%. Dark matter accounts for 27%. The majority of everything that exists and drives the behavior of the cosmos is something we cannot detect, cannot interact with, and cannot explain. It does not clump. It does not form structures. It appears perfectly smooth, uniform, filling all of space with constant density, exerting its repulsive effect equally everywhere. The leading theoretical candidate for dark energy is vacuum energy, the energy of empty space itself, represented in Einstein's equations by the cosmological constant he famously introduced and then abandoned. When theoretical physicists calculate what the energy density of the vacuum should be from first principles using quantum field theory, they obtain a number. When they compare that number to the observed value of dark energy, the discrepancy is 10 to the power of 120. That is a 1 followed by 120 zeros. It is described without hyperbole as the worst prediction in the history of physics. Our deepest theory of matter and energy, quantum field theory, and our best theory of gravity, general relativity, do not merely disagree on dark energy. They disagree by the largest margin ever recorded between a theoretical prediction and an observation. Alternative theories have multiplied in the absence of a solution. Quintessence proposes that dark energy is not a constant, but a dynamical field, one that changes over time and varies across space. Modified gravity theories suggest that Einstein's equations break down at cosmological scales and need to be replaced by something more general. The Hubble tension, the persistent disagreement between different methods of measuring the universe's expansion rate, has led some cosmologists to propose that dark energy's behavior is evolving, that it may have been different in the early universe than it is today. None of these proposals has been confirmed. New data from the Dark Energy Spectroscopic Instrument and the Euclid satellite are actively testing some of them, but no resolution has emerged. Dark energy's effects are exclusively intergalactic. Within galaxies and within galaxy clusters, gravity still dominates, holding structures together. But in the vast spaces between galaxy clusters, dark energy is winning, pushing the universe apart faster than it was yesterday, faster than it was 1 billion years ago, and slower than it will be 1 billion years from now. Galaxies beyond our local group are already accelerating away from us. Given enough time, they will cross our cosmic horizon and vanish, unreachable and unobservable forever. The universe is not merely expanding. It is being systematically disassembled, structure by structure, by a force that constitutes 68% of everything and that we cannot explain with a single confirmed equation. We do not know what dark energy is. We cannot detect it directly. We cannot stop it. And every second that passes, it has already won a little more of the universe than it had before.